In this video, I will describe a new structure that is based on the 5 spherical platonics that we've already seen, and these are referred to as polydesics. The geodesic arc of a spherical polyhedron can be projected down towards the center to form a polydesic section, which partition the sphere's volume into identical wedges. This is the tetrahedric. This is the hexadecic. This is the octahedric. This is the dodecadecic. And this is the icosahedecic. Now we've already derived the spherical angles for the faces of these sections in an earlier video. And in this video, I'll show you how to calculate the subtending angle of these polydesic sections. We will use some basic spherical trigonometry to do so, which I will demonstrate in the following slides. Once we have calculated the subtending angle, we can mark subtending angles with folded lines on a circular plane, which then can be formed into these polydesic sections. And an arrangement of these polydesic sections can be assembled to form a complete sphere, as here in the tetrahedric. The spherical law of cosines will be used to calculate the subtended angles based on the spherical angles that we've already derived for each of the spherical platonics. These are the 3 trigonometric formula that will be used to calculate the subtended angles we need to construct the polydesic structures shown earlier. Uppercase letters A, B, and C represent the spherical angles, and lowercase letters A, B, and C represent the subtended angles. For each spherical platonic, we will calculate the subtended angles for the associated polydesic section. So let's start with the spherical icosahedron, of which we know the spherical angles are 2 pi over 5, as seen here. We now take the values for the spherical angles and substitute them into the following formula. Since all the spherical angles are equal, we only need to solve one of them to compute the subtended angles. With some simple calculations, the subtended angle computes to approximately 63.435 degrees. Now we can mark off these 3 angles on a circular plane to create a template for an icosahedric section. And once assembled, 20 of these icosahedric sections will form a complete spherical structure known as an icosahedric. Now let's look at the spherical octahedron, of which we know the spherical angles are pi over 2, as seen here. We now take the values for the spherical angles and substitute them into the following formula. Since all of the spherical angles are equal, we only need to solve one of them to compute the subtended angle. And with some simple calculations, the subtended angle computes to 90 degrees. We can now mark off these 3 angles on a circular plane to create a template of an icosahedric section. And once assembled, 8 of these octahedric sections will form a complete spherical structure known as an octahedric. Now let's look at the spherical tetrahedron, of which we know the spherical angles are 2 pi over 3, as seen here. We now take the values for the spherical angles and substitute them into the following formula. And since all the spherical angles are equal, we only need to solve one of them to compute the subtended angles. With some simple calculations, the subtended angle computes to approximately 109.47 degrees. We can now mark off these 3 angles on a circular plane to create a template of a tetrahedric section. And once assembled, 4 of these tetrahedric sections form a complete spherical structure known as a tetrahedric. So we've seen how to calculate the subtending angle for polygons with triangular faces. And we used the law of cosines using the spherical angles to calculate the subtended angle. This gets a little more complicated if the face is a square or other non-triangular faces. So first we need to partition the square face into triangular sections so that we can use this in the law of cosines. So I've drawn in the edges of the octahedron here on top of the spherical cube, and we can extract some information from the spherical octahedron to use. We know its spherical angle is pi over 2, making this angle here pi over 4. You know this line is perpendicular. That becomes pi over 2. And this angle here represents half of the spherical angle of the square face, making it pi over 3. And we'll use this triangle for our further calculations. This is the triangular subsection we need to work with. And it's the vertical edge that represents 1/2 of the edge of the square face of the hexadecic. So in the end we need to double this length to get the full length of the square edge. We can now substitute these spherical angles into the formula for the subtended angle C, in this case, highlighted below. Then with some simple calculations, we can compute the value for C and then double it to get the subtended angle for the hexadecic, which is 70.53 degrees. And now we can mark off 4 of these angles on a circular plane to form a template for a section of the hexadecic. And once assembled, 6 of these sections will form a spherical structure known as a hexadecic. Now let's look at the spherical dodecahedron. Since its faces are pentagons, we'll first need to subdivide it into triangular sections by overlaying the edges of both the spherical icosahedron and dodecahedron. We then can further subdivide these sections to form this triangular section. The values for the spherical angles are half angles of the icosahedron and dodecahedron. The vertical edge C here represents 1/2 of the edge of the dodecadecic. We can now use the angles to calculate the subtending angle C. We then need to double it to get the subtended angle of 41.81 degrees. We can then mark off 5 angles for the template of the dodecadecic section. And once assembled, 12 of these sections will form a spherical structure known as the dodecadecic.